And now it's time for our final presentation, which is by our research engineer, Bogdan Cebere. It's on Adjutorium, which, as I'm sure you'll see, is basically a way of taking a lot of the work that you've seen to an entirely different level. So Bogdan, whenever you're ready, please go ahead and share your screen.
In this presentation, I will talk about Adjutorium framework and AutoML tool for static data. But first, let's do a short recap of the terminology. AutoML is the process of applying machine learning models to real-world problems without any special expertise in the field. The main goal is to empower anybody to use ML, giving access to a wide range of algorithms. And the offer in the AutoML field is quite rich, with a lot of options to choose from. And the natural question that might arise here is, why do we need another AutoML tool? As you saw in the presentation so far, new ideas are developed in a fast-paced rhythm. However, it is not trivial to bring them to daily use, mostly due to access to real-world data. Another problem is that not all the relevant tasks for healthcare are covered by the existing AutoML tools, and you might need to design or write the optimization objectives yourself, which is not pleasant. Another big issue is that you need to bring the data to the AutoML core logic uploaded somewhere in the cloud, which is a significant bottleneck from a privacy point of view. Maybe the most important point is that interpretability is a must in this field. So we ask ourselves, why not bring the best models to the data instead? We designed Adjutorium, an AutoML library for static data with clinical use cases in mind. The high-level design follows a well-known pattern and is based on prior research from our lab, such as autoprognosis or survival kills. The main goal is to create a bridge between the latest research and real-life use cases. The library offers a Python API that allows you to run a wide range of experiments. However, it's not the only way to use it. We also offer an UI on top of it, which can be deployed on-premise. It requires no programming knowledge while keeping all the relevant information accessible. We will now demonstrate the capabilities of the Adjutorium framework. The tool is available as a standalone Python library, and it provides a plethora of options on top of the AutoML logic. Here you can see a short example for using it for survival analysis studies in a script. The framework includes a user interface as well. The UI can be deployed as a Docker image as documented here, which is more convenient for cloud environments. Or you can simply start it as a script, as we will do next. Internally, it starts a worker which is responsible for the AutoML part, and the UI component which we will explore next. On the main screen, you can see a list of prior experiments, and we will walk through the process of creating a new study. We will demonstrate the capabilities using the QTrack dataset for prostate cancer, which we are exploring for a project in collaboration with Vincent Pragasan, university lecturer and consultant urologist at Cambridge University Hospitals NHS Foundation Trust. The dataset consists of 10,000 patients, and we will explore it in a survival analysis setting using the time to event or censoring data. Next, we will start a new study. There is a set of mandatory rules for uploading the data, such as the dataset file format. For each task type, we are required to provide some special information in the dataset. For example, in the survival analysis setting, we are required to provide outcome and time to event data. Now, let's upload the dataset. On the right, you can see a summary of the task, and you can double check that there is no mistake in the input. This short recap includes how many subjects and covariates will be processed, their type, and which ones will be encoded or imputed. There is also mentioned if columns will be dropped due to excessive missingness or invalid format. We can see details about the algorithms and tools underneath, and we can further customize them in the advanced settings section. Here we can customize the evaluation horizons, imputation, explainability, or prediction methods. For this short demo, we will ask the optimizer to evaluate mice and mean imputation methods along with XGBoost and CoxNet prediction models. That means that the AutoML logic will search for the best parameters for these algorithms in the given dataset scenario. For the final plot, we will split it using the treatment column. It will be more clear in a few minutes. This concludes the setup process, and it's time for the model search. This step searches for the best parameters for the task. It will reuse prior knowledge if available and run different scenarios for each of the selected time horizons. The first section here includes some graphs about the observed performance from all the trials for all the relevant metrics such as area under the curve, concordance index, or calibration score. We can see the performance range and the outliers, and it is useful for understanding if a certain dataset has good support for the selected outcome. In the next section, we will see a more detailed breakdown of the evaluated pipelines. We can see details about the imputers, the preprocessing techniques, or the algorithms. Due to usability constraints, we cannot show the full parameters, but just some short name. Each row here is evaluated with different parameters picked by the Bayesian optimization underneath. Once the optimization process has a candidate that is above a performance threshold, you will see this button on the right enabled. Otherwise, it will keep searching. And since this is a pretty flexible library, you can use the REST API to see full details about the selected model. On the left, you can see runtime logs from Adjutorium, the Adjutorium worker. On the right, we will query details about the final candidate. The breakdown includes the base models used in the ensemble weights, but also the full signature of the final model with all the parameters. It might be clear now why this is hard to display in a user-friendly way, but all the information is there. The build step will train the final model and explainer and build an app around it, which will be available on the main screen. Here we can start exploring our study. The left menu is generated based on the provided dataset, and on the right we will see the risk estimation graphs as well as the feature importance at each time horizon. The graphs are split around the treatment column, and as we selected in the setup process. Thank you for listening.
So I wanted to really highlight this, especially this last piece of work that Bogdan has presented, which represents a tremendous amount of work done by Bogdan in a very short time, where he took many different models that our lab created for time to event analysis, survival analysis, but also for prediction. And really, I would say he created an ecosystem that really can be tried at home by novices, where indeed somebody can just drop in a data set and the data set is evaluated, and then it passes through this entire pipeline of imputation, feature selection, predictions, calibration, and interpretation, all the way to creating a visualization. So I think that this is very powerful because currently a lot of this work is happening, number one, by hand in many scenarios. So finally, we can now take this to the next level to really try it on many diseases. So we have multiple collaborators and funding from a variety of charities and healthcare organizations that I hope could tap into this resource that we have built to try to build predictions and risk scores to empower clinicians and patients using this particular technology. So again, you can feed it different types of data sets and create useful resources and useful tools. So I really would like to draw your attention to this particular piece and thank Bogdan for tremendous amount of work that went into this.